Algebra 1 students, welcome to your 4.4 notes, graphing a function rule. We're going to look at lines, we're going to look at continuous graphs and discrete graphs, the difference between those two. And we'll talk about how they change. I mean, that's what we're doing after all, is we're waiting for the graph to change. So let's take a look at this. A continuous graph is a graph that's unbroken. The way I would suggest thinking about it is you could graph the entire function or rule without picking up your pencil. You can see that right here. A discrete graph is a graph that's composed of distinct isolated points. You see an example here. They don't have to be in a linear fashion. You could have a point like down here added into the mix, or you could have one that's up here, or you could have one way off like all the way down here. It doesn't really matter, but it just simply means they're points that are not connected. Now I will say most of them that we see today, what we're going to see today, is in a linear fashion, but discrete. Alright, and again we'll talk about more of the application in a moment when we get there. Alright, I want to introduce you to some parent functions, the absolute value function, the quadratic, and the cubic. The absolute value is y equals the absolute value of x. You can see it's got a distinct V shape. As soon as your term that's inside the absolute value bars becomes 0, it causes the graph to turn around. So that graph has that V shape. The quadratic is always either going to be opening upward or sometimes downward. We could see examples of that as well. Where the cubic, it's like a little bit like a quadratic, but one of the sides is twisted and turned upside down. It's also a little steeper, which is kind of hard to tell without a little closer analysis. But you can see the shapes of those three, and that's basically the three different graphs we'll be focusing on today, outside of the linear graph, which we'll also focus on. So let's take a look at a linear graph right here. We got a couple of them. The first one, y equals 2 minus x. We're going to graph the function. Here's my advice for you. Let's go ahead and plug in values, and quite often the values we can use are these numbers: -2, -1, 0, 1, and 2. There are times where we'll have to get away from those numbers just a little bit, but what we're doing today, those are a pretty good start. So 2 minus -2, that's the same as 2 plus 2, which is 4. I'm just plugging these values into the equation or the function that's up here. 2 minus 0 is 2, 2 minus 1 is 1, and finally 2 minus 2 is 0. So again, just make up values for x. We like these values, but others would work as well. And then plug them in to your function. So, and then now we're going to graph -2 and 4, 1, 2, 3, 4, -1, 3, 0, 2, 1, 1, and then 2, 0. Now you'll note that these are a linear function. We could go ahead and sketch the line that connects these to each other. I've missed just a little bit. The good news is I can fix it. There it is. So it would look something like that. Alright, why don't you guys do this? Why don't you pause the video, try to do number 2 on your own. When you're finished with it, hit play and see how yours compares to mine. Alright, welcome back. If you take a look at my graph here, you can see that I've again plugged in the values, the input values of -2, -1, 0, 1, and 2, and I've connected them. You can see the results here. Again, with a line, it doesn't necessarily have to be those 5 points. As a matter of fact, with a line, even just 2 points would be enough to get a reasonable graph. Alright, let's take a look at this. The cost in dollars for a health club membership depends on the number M of whole months in which you are a member. The situation is represented by the function C equals 49 plus 20M. Alright, so this is the function right here that we're going to graph. Now this says X and Y. I'm going to change it as M is my input, C is the output, or the dependent variable, M is the independent variable. Now in the situation here, we have to think about reality. What's the shortest amount of time you can be a member of a club? Well, I mean, I guess 0 would work, sort of. You can't do less than that, that's for sure. You can't be a member for -2 months or something like that. Doesn't really work. And it's questionable if 0 even works, because when you plug in 0, you get 49 plus 0. So you pay $49 to be a member for 0 months. Not the best investment, I'm going to say. But I'm going to go through and plug in these values. When I plug in 1 and 2 and 3, I'll see that my price increases by $20 each time. Now I want to go ahead and graph this. So let's see here. Let's do 1, 2, and 3, and this of course is number of months down here, and then over here is the cost. Now let's see, let's do like 10, and then I'm going to go a little bit bigger gaps there, 30, 50, 70, 90, 110. I better label some of these. There's 30, 50, and so on. And you could label this in different ways than I do. I just was trying to get some values that would be easy to spot. Okay, so 0 and 49, just going to approximate very close to 50 there. 1 and 69, very close to 70. 2 and 89. You have to remember on a graph like this, it's a pretty rough graph. I'm just doing this on my own. It looks like I made a mistake on my label over here. So don't be in a panic if it looks just a little bit off and like, whoa, that's not exactly linear. If you know it is linear, that's okay. Now, here's the question that we have to follow up with. Is this graph continuous or discrete? That's the part that's a little different here. This graph is absolutely discrete. The reason being, you aren't paying for part of a month. It's the full month or nothing. So it's not a line, it's a set of discrete points. There it is for 0, for 1, for 2, for 3. So there is a linear pattern, but it's not a continuous pattern. We can't do 1.73 months. They don't offer that. It says whole months. So we're going to make it a discrete graph. We're paying 1 month at a time. Again, pause the video. Try working through number 4. It's a little tricky. It's application. But see how you do on number 4 and then compare your answer. You can see my work on number 4 now. This is a continuous graph this time. Let's talk about that for just a minute. Why is it continuous? Well, it's continuous because unlike the previous problem, I could do partial amounts. In other words, when you purchase bananas, it doesn't have to be exactly 1 pound. It could be 0.23 pounds or a fourth of a pound or a half of a pound. It can be all kinds of numbers in between 0 and 1. So in this case, we connect the dots, where the discrete graph is one where you can only purchase set amounts, okay? And so it can't be the in between. You can't do a half a month at the what was this up here? The health club membership. Whereas you could definitely do half a pound of bananas. And looking at this now, I've realized I failed to label my x-axis. I put the label, I guess, but not the values. There it is. All right. Let's take a look at the next one. This time we have an absolute value graph to consider. As I mentioned earlier, good numbers for you to choose would be numbers like -2, -1, 0, 1, and 2. That varies a little bit from time to time, but we'll look at examples. For what we're doing today, these are pretty good values. So the absolute value of -2 is 2. Add 1 and you get 3. Absolute value of -1 is 1. When you add 1, you get 2. 0 plus 1 is 1. Absolute value of 1 plus 1 is 2. And we're going to see the pattern start to repeat itself from what we did when we were less than 0. So let's do this. -2, 3. -1, 2, 0, 1, 1, 2, and 2, 3. Now, that is your absolute value graph. I mentioned this earlier, but it's a distinctive V shape that we have going on here, so it should look something like this. There it is. All right, why don't you, again, for the penultimate time, pause the video, do this next problem on your own, and then see how your answer compares to mine. All right, again, I'm back, and you can see the work here. One thing you'll notice, I actually went beyond 2. I went -2, -1, 0, 1, 2, but I realized this pattern bottomed out at 1, and then it started moving back up. So I thought doing 1 extra point will give me a little bit clearer graph, so I went ahead and plotted 3. Now I could have kept going and plotted 4, 5, 6, whatever, but that was good enough. for this one as far as I was concerned. Alright, so let's take a look at our last slide. We got a cubic graph and a quadratic graph to consider. So on number 7, y equals x cubed plus 1. Again, the values from -2 to +2 are pretty good values to pick. Remember, when you cube a negative number, that means -2 times -2 times -2. It stays negative. That's -8 plus 1, which would be -7. -1 cubed is -1. Add 1, you get 0. 0 cubed plus 1 is 1. 1 cubed plus 1 is 2. And then 2 cubed is 8 plus 1, or 9. I know I'm doing that a little bit quick, but you guys are fast learners, so I'm assuming you'll be able to pick up what I'm doing here. What I'm doing now is plotting all those points that we just saw. I'm going to have to do a little bit of estimation. 2, 9 is obviously off the grid, but we can figure out an approximation of where that point would be. And we have our cubic graph. This graph is becoming a bit of a visual disaster for me. I'm just going to roll with it though. This is a sketch, not an exact graph by any means. Okay, I sort of made it better, sort of, being the key word there. Should look something like that. Alright, I was going to have you guys do this last one on your own, but I'll go ahead and work with it through it with you. I can't even talk right anymore, but I am a nice guy, so I'm going to work with you on it. Y equals -x squared. Now remember, the exponent happens before the minus sign. Think of that as subtraction. So -2, when you square it, you get +4, but then you have to make it negative. So that's -4. -1, you square it, it's +1. Change the sign. 0, you square it, and it stays the same. When you square 1, it becomes 1, or stays 1, but then you have to change the sign on this one, and you have the same situation with +2. There's a lot of symmetry on quadratic graphs. There's actually symmetry on all these graphs we've been looking at today. Linear, absolute value, quadratic, cubic, all of them have symmetries. They're a little different, but they all have some symmetry there. So if you look for patterns, you can often find them, and then repeat those patterns, save yourself a little time. Alright, so this one looks something like this. That one wasn't quite the disaster of my cubic graph. Not perfect, but that's okay. I'm not looking for perfection. I'm looking for good sketches. Alright folks, that wraps up your 4.4 notes. Again, do your best to get this figured out. Fill out all those notes. If you have any questions, come ask me in class next time we meet. You guys have a spectacular day and come ready to work.